Okay, well, first of all, let me thank the organizers for inviting me. This has really probed the impact of quantum processes and the treatment of quantum processes and biological problems. So what I want to show you is my opinion, well, discuss also my opinion about the QMMM simulations. I think they're going to become increasingly important to be able to look at enzymes, not only their active sites, but how they dock with one another. And through those examples, because it's going to become much faster through GPU computing, you'll really be able to study whether there are any quantum effects that we need to look at, besides the obvious one when you have a chemical reaction taking place inside of an enzyme. So I was going to show you, this is what I'm going to present to you was some work that we published in Nature Methods in the spring. We looked at a particular reaction. It was the one that sets the genetic code in all organisms. And let me first just review with you very quickly what are the protein RNA complexes that are in translation. There are these synthetases. This one is the one for aspartic acid. It's supposed to recognize the tRNA for aspartic acid, so it's recognizing it at the anticodon region here. Once the tRNA, and what does it do? It reads the anticodon, and then it puts the aspartic acid here at the tip of the CC end of the tRNA, and then it gets picked up by the EFTU, and then taken to the ribosome. And now you can see it's reading the messenger, and there are already 3 of these on them. And of course, we've decreased in size. And if you want to continue on modeling translation, you have to realize at least in even any small organism, there's at least thousands of these ribosomes you have to consider. But we're going to concentrate on this first part. This step here where you set the genetic code. This is the only place that it's done. Here you have to get the right amino acid onto the right tRNA. If you don't do it there, there's nothing to correct it as you go further. All right. So I just went through very quickly. If you're interested, I've been working on this for many years. Almost every one of these steps have been done in collaboration, also with Carl Vos. So he's a co-author on one of these several of these papers. And these are just some of the simulations of the motions that you would see, say, in the tRNA when you have very low magnesium conditions, a very high magnesium condition. So there's lots of fluctuations in them. You can do a typical molecular dynamics simulation on it, put everything into a big box, add the ions. These are all the parameters that we use to do it. And what I'm really interested in is this part here, the so-called anticodon arm here. It docks with the anticodon domain, and there's a few other places where it helps to recognize the right protein. But what happens is you put the amino acid up here, and that's about 50 angstroms separated from the main identity element. The overall reaction that we're talking about is you have ATP and glutamic acid, in this case, going into the active site of the synthetase. It's going to charge the amino acid and then put it onto the tRNA. And as I said, this all takes place within the active site of that synthetase. Now, what we did in the Namdigo's quantum paper, we have now integrated quantum mechanical packages, several of them. One is sort of the leading ab initio program called ORCA. It's from Frank Nessa, and another one is a semi-empirical method called MOPAC. And again, here's the reaction in schematic form. All the components are coming into the active site here, and we're going to be really looking at these 5, 6, and 7 steps here, making that reaction. And one of the things that we wanted to study here was when you're adding the charged amino acid onto the CC end of the tRNA, does it attach to this, the 3' or the 2' hydroxy? There have been various theories about which it should be, and I won't go into that, but we thought we could study this. We could also look at the effect of proteination on the amine group. This is also important later when it gets into the ribosome and is incorporated in the growing chain. So those are the type of questions we wanted to probe. So first thing is that you have to decide when you're doing a QM/MM calculation, what part will you do quantum mechanically? We're still not at the point where we can do the entire complex quantum mechanically. So you have to decide what's important. And one of the ways that we do it is by trying to do what is called a network analysis. Look how the parts are correlated with one another. And so you have to build a network. You're doing a molecular dynamics simulation. You can do it just classically or a QM/MM calculation together. And you build a network. So the network has nodes, and our nodes are going to be put at the positions of the C alphas on the protein and maybe the phosphates on the nucleotide. And now the nodes have to be connected by edges, and you draw an edge if any heavy atom within that side chain or on that nucleotide are in contact during, say, 75% of the simulation. Now, let's say this was the anticodon domain, and maybe this is the CC end of the tRNA. And you can see there are various paths that lead there. Some are longer than others. So this would be, if this is 10, this would be 10 and 11 steps to get there. So one of the things that you do, let's weight those edges by correlations. So you can go in from the simulations, and again, these can be QMM or just MD simulations, and calculate the correlations. So I know you can't read this, but it has the tRNA and the protein here, same thing here, and you're looking at the correlations among the atoms in this. And I can draw it here, the edges of this map, unweighted so far, and now let's weight them with correlations. And you start seeing some modularity forming. You definitely see this region really jump out at you. And what we're going to do, those lengths, those weightings that we use, they're related, as I said, in this case to the Pearson correlation, but you can use generalized correlations. And then the weights are proportional to the logarithm of their absolute value. And when you talk about an optimal path, you're looking at the one that has the lowest weights here to get from, say, here up to here in terms of the correlations. So let's look at those quickly. Here's an optimal path along with closely related or suboptimal paths. And now that is the optimal path. And let's just take a look, rotate it around. And you can see here's the main path, but there's some others that are close by. And if you wanted to, you could try mutating something and see if it did take one of these other paths. All right, so now, what about those modules that we saw? You can, again, figure out where they are from the correlation maps. You borrow a technology out of social sciences where they're always looking at what sort of groups are we members of. So they can call them, and then they build them into communities. And the way they do is the algorithm that we used initially was called the Gurman-Newman algorithm, where you go in and start cutting bonds and see if things break apart into groups that are more correlated within than between. All right, so this algorithm obviously said there are these three communities. Now let's go one step further. Let's zoom in now to that active site. Here's the CC end of the tRNA. Here's our charged amino acid. It's this adenylate here. And when the reaction takes place, whether it goes, it's going to attach to this OH. Then you'll split off the products, and you'll have the AMP being leaving, and you'll have the tRNA now being charged with the amino acid. This calculation, or this system, was first studied by Tom Steitz, who just recently passed away. And you probably all know him from his Nobel Prize-winning work on the ribosome. But he also looked at these a very long time ago. So now let's go take a look at those simulations. And so that's the system we looked at. Let's zoom into the active site. Let's look at the networks that connect to the major players there. And we'll zoom in further. So those represent two complete communities. And now you'll see that there's one community that is actually containing the amino acid part. And then there's another community that is actually containing the AMP part. So it almost tells you how things will break apart. And it gives you a good first suggestion what residues, what atoms you would like to include in the QM calculation. Now, we weren't able to use all of them when we did the paper. First, we just wanted to do a quick example, but then the reviewers kept asking more and more and more, can you calculate the free energy for this? So we did a somewhat reduced system, and this is what I'm really talking about, what we've added to the molecular dynamics is we've picked out a QM region. As I said, you pick it out by the network theory. You also have to be sure that the charges are not too great within the QM region. You'll have to connect this QM region to the MM region. You typically do that through what is called a link atom here. So it'll be at this interface here. And then you'll have to decide how you handle the charges in this local region. And I'm telling you, it's like a religion. There's Protestants, there's Catholics, Episcopalians, how you should handle the charges here. So we wanted to be agnostic. So in our programs, we allow you to pick one of the 6 popular ways of handling the charges in that local region. So again, let's zoom in. Let us say like this is our QM region. So that means you'd think of it being broken here to the classical region. You'd have these link atoms, these hydrogens. And now what the program figures out is how to trade forces back and forth between the QM region and the classical region. And as I said, these are sort of the charge redistributions. So again, that dotted line could represent the boundary between the 2 regions. You put the pseudo atom in there, and then you have various choices whether you count the charges on these guys or ignore them or go one step further. So these are all typical methods that are used in the literature. So now we want to study that reaction, and the way that we do it is picking out certain reaction coordinates. So we're sort of forcing the attachment here either to the 2' or the 3', and so as you see here, so those are those 2 cases here, attachment either to this side or attachment over to this side. And with those reaction coordinates, you do small steps at a time, and then you sort of try to converge on a minimal path. You check it then by doing a free energy calculation on this path using these path collective variables. For people who know QMMM, these are the Z and the S variables that you do this. And the choices that we had here in doing the string method of trying to converge to a first approximate minimal path really depends on we could actually parallelize this. So we used methods that lent themselves to using multiple cores on the supercomputer centers. Okay, so just to give you a feel for the reaction coordinates, because we wanted to compare the 2 different scenarios, we perhaps took more than was absolutely necessary. So you're trying to see, we took the distance from maybe here to here, the distance from here to there. All told, we had 7 different collective variables or reaction coordinates that we looked at. And you can really tell as you progress through the reaction, and so you can have this image be like the progression from, is that some of them don't look like they're particularly useful. Like this is somewhat flat. You really wouldn't want to choose that as a reaction coordinate. You want something that's a bigger change, like the blue one that tells you, yes, I'm on one side, no, I'm on another side. Okay, so this is again, as you go through probing at each of those steps, you can see the string sort of converging here on a path. And then, as I said, we put that path and then we examine it through one of the free energy method. This is called an extended adaptive biasing force calculations. And we looked at like 4 different scenarios and tried to see which one had the lowest barrier. And it turned out it was this one, adding it onto the 3' OH here. But as you can see, the reaction, the energy didn't really go down enormously after the attachment took place. And that's because you really have to wait for that group, the AMP that is leaving, to get hydrated and to move out of the pocket. And that hydration step, it's about at least 8 angstroms from where it was initially attached. And that is energetically gives you this big boost that you have overall at the end of this about a 15 to 20 kcal drop in energy. All right, so everything I've talked to you about, I can show to you in a quick movie. Whoop, I think it's going. So again, we're defining where the reaction, where the active site is, the allosteric pathway, and now we'll zoom into the active site. And what we're going to show you is actually the change in the orbitals as the reactions take place. All right, so now we zoom in, and you should be seeing the AMP moiety, the amino acid, and the CCA of the tRNA. So it's labeled here, thank heavens, so you can see it. So what we want to do is attach that and break this. And what I'm going to show you through the whole reaction are just the highest occupied molecular orbitals and how they change. So initially, they're relatively far away, and then we're probing them, getting closer and closer. So don't blink at the end or you'll miss the attachment. And now you're getting the transfer of this hydrogen over to here, to this oxygen on the phosphate. So this will leave as AMP with a proton. And then this bond will be formed. You already started to see some action. So this bond was formed. And now this bond will form, and this thing will cleave, and it will leave. So I don't know. When I first started to watch these, I thought, this is cool. I wish they had done this in my quantum mechanics class, because it really gives you a feel of what's going on and how that reaction is influencing the molecular orbitals of other part of the system. But we've, as I said, zeroed in on just a few of them so that you get an idea of what's happening. All right. So actually, the lead people in this will be the next speaker. That's Raphael Bernardi, and then he is a research scientist at the Beckman Institute. And then there's Marcelo Mello. He was my student, and he did much of the programming of connecting the QM interface into our molecular dynamics program, NAMD. And as I said, it took a small village to do this. So these are all the key players in the system. And as I said, we were extremely fortunate to have the lead author of ORCA, that's Nessa, and then we had Gerhard Rocha. He's leading, he's one of the main programmers for MOPAC, but more importantly, he's the one that's putting it onto the GPUs. So these simulations, we're hoping, you'll be able to do them in maybe 100 times faster than what we were showing you within a year. Okay, and with that, I'd like to thank you for your attention.
Thank you very much. Questions?
Why not use the GPU to expand your QM region and test the impact of more atoms in the QM region? That seems to me to be
We will definitely do that.
The critical thing here. And
it's just that as we started these reactions, the study, NAMD had not completely been GPU accelerated. That is just now being completed, and more importantly, MOPAC hadn't been done. He's not releasing that code until now. We are working already, I don't know if you know him, Todd Martinez, sort of in your neighborhood, for Therachem, so that'll be another interface. So as I said, I'm hoping this will be such an efficient code that everybody who wants to probe the system will be able to do it. You're totally right. I think with the GPU, we can expand it to really do the communities that we saw through the community analysis.
So I may have missed, did you actually do this? So you said there are two QM programs, so MOPAC and another one.
Yeah.
And one is ab initio, right?
One is ab initio, that's ORCA. So that has all the high-level DFT, Hartree-Fock, you name it.
So did you try comparing the two approaches?
Well, we compared them in obvious ways in terms of energy conservation, but timing. Okay, MOPAC is incredibly fast because it's semi-empirical and has been parameterized some of the interactions. But if you have Therachem, that is supposedly about a factor of 50 faster than the present ab initio programs.
Right. So the idea, of course, you want to. sure it gives the same results as.
There have been studies and about comparing the quality of the results. As I said, with the free energy calculations, those are part of the NAMD goes quantum nature methods. We did all the comparisons that you'd want to have, also for all the different choices of the charge redistributions. Very comparable. You always worry about a semi-empirical method, but you would be crazy not to do that first, just to probe a scenario.
Yep.
Mm-hmm.
Other questions?
You got this. Now let's talk about science. You did this calculation. You saw these different regions on your tRNA.
Uh-huh.
Can you use that to make some comment about fidelity?
You know, interesting. So Rafi will talk more about using multiple QM regions and looking at an even more challenging system. You know, we didn't think about doing that. We should, particularly because we do know there are some, quote, mischargings that can happen. Like if you have leucine, can you sometimes put isoleucine in there? How is that changed in the active site? So we are doing that, but on the LURS. With the aspartic acid, there weren't any good experiments. We do have some experiments on the LURS and then can now look at that, right?
Any other question? If not, let's thank Zan again.